Alrighty, thank you very much for the chance to talk to you. This is a talk given on behalf of myself and Marc Paterno, who's sitting there. Basically, we'd like to give you, sort of describe the problem space that we're faced with and how we're dealing with it. And ultimately, we'd be interested in ideas, sharing not only our ideas with you, but your ideas with us, so we can help make things better, not only for us, but for the Spack community in general. So before doing that, let me provide a little context of what we're doing. I'll talk about Fermilab first. It's about 30 miles that way, I think. So it's not far. And so it was pretty convenient for us to attend the HBSF conference this time. What Fermilab is pretty much the only DOE complex that is a single-purpose laboratory. So it has this rather grandiose title of being America's Particle Physics and Accelerator Laboratory, bringing the world together. And I mean, the purpose for that is that's all it does, is it's particle physics. It might be through high energy physics using accelerators and things like that, or it might be through cosmology and doing astroparticle physics. But it's all looking at fundamental physics and trying to determine basic properties of the universe. So the biggest landmark here would be Wilson Hall, and there's also an engineering research center, which is I don't know, which is sort of in the foreground. Right now, they're in the process of upgrading their accelerator system into having more intense proton beams, which eventually means you can create more particles of interest, neutrinos in our case. So yeah, happy to talk more about this if anyone is interested. But that's basically where things are. So the biggest project that Fermilab has on its docket right now is called the DUNE experiment, which stands for Deep Underground Neutrino Experiment. And the purpose of that is to look at how neutrinos morph from one kind of neutrino into another kind of neutrino after it's been traveling through the Earth over a long distance. So perhaps hopefully this caricature gives you some idea of what's going on. In Illinois, we're creating all these neutrinos, and then we want to detect how the neutrinos start in a particle detector, still in Illinois, but then we shoot the neutrinos straight through the Earth into South Dakota. There's what we call the FAR detector over there. And by looking at how the neutrinos change from Illinois to what they're registered as in South Dakota, we can make some interesting conclusions in terms of the physics. So the NEAR detector is kind of big. I don't know if you can see, there's this guy way on the far right. Boy, I don't really have a, oh yeah, I do. Okay, yeah, he's sort of around here. So, we're talking about large apparatuses here. But that's the NEAR detector. It's a lot smaller than the FAR detector, which is over here, and the people are quite small over here. We're dealing with neutrinos that don't interact with hardly anything. So if you want to be able to detect them, you need really big detectors. So this thing is gargantuan. The whole project costs like $3 billion. And the hope is to detect one neutrino interaction, like I think it's one a day. So it's not a lot. But from doing that, you still get enough physics information that you can make some definitive physics statements. So we are tasked with providing the computing infrastructure so that physicists can perform these types of experiments. So the vast majority of our user base are these types of people, the actual people who will be working on the experiments themselves. They're not experts in computing. If you ask them, what operating system are you running, they might say, what? I mean, they may be a little bit better than that, but really, I mean, they think in terms of the physical experimental device there and mathematical equations and physical relationships. They're not specialists generally in computing. So how do we support them now, and then how are we going to support them moving forward? So we have been supporting software stacks at Fermilab for a few decades now through our own package manager that we call the Unix Product Support, or UPS. It has worked pretty well, but we just don't have the effort to continue doing it. And Spack was very attractive to us because it checked off all the boxes that we required, and it was supported by a much larger community than our rather parochial group of people in high energy physics, specifically at Fermilab. So we looked into Spack, I don't know, 7 years ago or so. And it has been largely successful. One of the most difficult parts is that it's a large mind shift for our users. They're not used to operating this way. So that's been a hurdle that we'll continue to have to deal with. But a lot of progress in the last few years. We now have proof of principle installations for all the offline code. And by offline, I'm referring to the code that is not responsible for collecting the data in those huge detectors I showed you, but, or not in real time, but analyzing the data after all that initial data has been collected. So we do have installations with Spack for all of our, many of our experiments. So Dune is the big one I already told you about. There's also something called Muta-E. There's SB&D Icarus, and I can tell you about a bunch of others too. So you'll hear tomorrow about how Spack is being used by data acquisition systems. Eric Flemmerfelt will talk about that tomorrow. Fermilab also joined the technical steering committee. Mark you may have seen his picture earlier when Todd was giving the overview of Spack. So we're in the midst of establishing a process for layering releases and what will become environments for Fermilab supported software. And we are very interested in finding solutions to the development problem. And I'll get into that with what we call Spack MPD. So I want to talk then about how we organize software into layers. We've been doing this for a while, but in order for you to have some background, I already told you that our users are physicists, but they're also physicists. They don't have access, or they have access to machines that give them very limited privileges. They certainly don't have root user access. They're shared machines. They have disk quotas, which if you're not careful, it's very easy to blow through your allowed space there. But they also recognize the utility of sharing software with other people. So it's not like you would go to a grad student and say, all right, I want to install Trilinos. Just go ahead and install it. They would never do that. Instead, they would have some type of release manager in the experiment who would give them explicit instructions that you need to invoke this setup script, which will point things to the right place, but under no circumstances will you ever be installing your own software unless you want to get in trouble. Just our user base tends to not be that careful in terms of managing their software. So instead, it's the computing professionals who do that, and the way we've done this in the past is come up with this layered approach. So what you see at the bottom are things that correspond to not just single packages, but they're like suites of packages. So ART is a computing framework that many of our experiments use. There may be 30 packages inside of there. FIFE is an acronym that stands for something you don't need to know about right now, but there's maybe another 30 there. And then New Light is built on top of these things and Larsoft on top of that. And eventually, if you're the Dune experiment, then you have a layer on top of that, which makes use of the products and all of these layers underneath that. So when we're thinking about Spack now, we're no longer talking about UPS. We're migrating to Spack. This approach in supporting the experiments and software layers, it still seems to map pretty well, not only in UPS, but also in Spack. It's just that the way we do this is going to change. How we did it with UPS is the art developers, for example, they specify, okay, you're going to use Boost this version, you're going to use Python that version, GCC, whatever, with the particular standard. And then the concretization, so to speak, happens in the head of the developer. Does this thing work? Oh no, I have a seg fault, probably the wrong version, so let me go back and figure things out. With Spack, it's much easier. However, it can also be a lot more difficult. Because, for example, the experiment Dune, maybe they want to use TensorFlow. Maybe they want to use PyTorch. Maybe they want to use TensorFlow and PyTorch in the same program, IC. But we have that sometimes. So how we've decided to do this is pretty much put the whole graph together all the way from the bottom, which we're calling tools, which will include the compilers, Python, all the way up to the Dune experiment, concretize the whole mess, and then we can divide things out a little bit so that if you're an experiment that needs larsoft and everything underneath it, but you don't need Dune, you can still use the larsoft environment. You would just include it in your own environment and move from there. Okay, so I want to talk about MPD, and this really came about as a need for meeting the development needs of our users, the graduate students, in a way that looked pretty similar to how they've been doing things in the past, to how people are doing things with Spack. So So what are we talking about here? I already mentioned that the experiments, they share code, which is good. But what may happen is one experiment may develop their code at the same time as they need to adjust another piece of software. So maybe, let's see if I can get the cursor. So if I'm a collaborator in the Icarus experiment, maybe I need to adjust my code in there, but at the same time I have to adjust the interface up in larsoft up there. We had ways of doing that with our own system that we called the multi-repository build system, MRB. And the way we would do this is if you need to adjust both, well, you just check out all those packages, not only the ones that are in larsoft, but the ones in Icarus, and you got to make sure you're doing all the things in between, right? Because otherwise you're going to have, one definition rule violations if you're not rebuilding everything in between there. And we had a way of doing this, but that could be kind of clumsy. Spack does this pretty well, right? You have the whole concretization graph. It knows what the dependencies are. Because all of our software that we support and that our experiments use is all CMake, we can do a lot of short-circuiting, so to speak. We can make a monolithic CMake project, which basically just does a whole bunch of add subdirectories of these individual CMake packages, treats it as one big CMake project, and you do one CMake configure, and you rely on CMake's ability to look at the dependencies of the targets inside the whole CMake package, and then it can wildly parallelize the build based on that. So it's been very successful, and especially whenever you have these shared machines that have limited memory or I guess, if you're sharing them with a whole bunch of other users, then it tends to be an efficient way of making sure you're not commandeering the whole machine when other people may need it, or the other way around. So unfortunately, MRB, though, has relied on UPS, and we're going to Spack. So we want something that's similar to Spack. Eventually, I would love to not have something like MPD, which is our Spack extension. But our users are not yet at a point where they can go straight to Spack. They need a little more help than that. So we want to minimize their knowledge of their required knowledge of Spack, and then take advantage of upstream Spack instances and some of the other things that have become very successful. And well supported in Spack. For usability, basically, if somebody wants to develop their code in different repositories, they create a project. It may be that while they're working on a project and trying to develop different bits of code, they want to switch to a different project. Well, that can be tricky if you rely on environment variables and things like that. So we found ways to get around that. Okay, time's getting a little short here, so I'll move ahead. But what MPD does is, again, it's trying to make it easier for the developer to create development projects while using Spack on the back end. So there's a bunch of commands here. They're factorized into project commands, so you can work on different projects. Development commands, I want to build stuff now, I want to test it, yeah, maybe I want to install it, but most of the time when you're doing development, it's an incremental build that everyone is doing. So that's what we're really focusing on with MPD. There's some usability commands, and then you have to initialize the thing. So just going to walk you through a quick workflow. So I have a project where I want to develop some of the art suite, for example. So I call my project my art devel. There's some boilerplate here. One of the things you might see then is that I want to base this project off of the GCC 14.2 environment. It's an existing Spack environment somewhere. It has GCC 14.2 in it. So I create my project. At this point, I can clone repositories that I actually want to develop. This is something that our users have requested the ability to do. And we also added the ability to fork the project on GitHub if you really wanted to do that. You don't have to. So now you've checked out your repositories you want to develop. You have to refresh everything because Spack needs to know that it's time to concretize. And so it's going to concretize everything for those repositories that you're going to develop. Eventually, it will say, all right, you need to install this stuff, yes or no, and then you move on. Once it's ready for development, you can actually build. So Spack MPD build, then it activates the development environment and goes through the CMake. You can then run a test command. You can also activate the environment explicitly and just go to the right directory and type ninja, if you like, once you've done the CMake configure, or ctest, if you like. And then you can finally install your project as an environment that can be used as a base environment for your next MPD project. So if you need to start layering things on top of each other, that's fine. And then there are other commands. What's my status? Sometimes I don't remember what project I'm developing. What projects do I have available to me? In this case, you only see one, but generally you would see a list, and it would highlight which one is active at a particular time. I'm short on time, so I think I'll skip some of our pain points. I think the biggest one is include concrete. We could use some more configurability there. So I'm happy to talk about that if there's any interest, but for sake of time, I think we can call it a talk. So thanks.